Welcome in the evening session. It is my great pleasure to introduce to you Professor Irena Lasiecka. She's a distinguished professor at the University of Memphis. She got the both master and PhD degree from the University of Warsaw, both in applied mathematics, then worked for some time in the Polish Academy of Sciences, and then moved to the United States, first to the University of California, Los Angeles, then there was University of Florida, University of Virginia, and now, as I said, she is a professor at the Memphis University. In 2011, she got the SIAM Prize, the Society of Industrial and Applied Mathematics Prize. It's called WT and Idalia Rate Prize for fundamental achievements in the control theory and the optimization, especially using the partial differential equations. It is worth to mention that she was the first woman to get this prize. And in 2019, she got Richard E. Bellman Control Heritage Award. And again, for 40 years of the history of this prize, she was the first woman to get that prize. So I already know that her specialty is optimal control theory and various applications, and we'll hear about them pretty soon. Just this year, she got the Hugo Steinhaupt Prize, the Polish Mathematical Society Prize in the main prize in applied mathematics. Professor Irena Lasiecka was an editor-in-chief of Applied Mathematics and Optimization, and currently is editor-in-chief of the Evolutionary Equations and Control Theory. And she's a fellow of AMS, American Mathematical Society, SIAM, and Institute of Electrical and Electronic Engineers. So as we see, this is very interdisciplinary and research she's doing, and well, without any further delays, we will hear your talk. So the Zoom is yours. So you can share the screen.
Ja, dziękuję bardzo za to wspaniałe wprowadzenie, także bardzo jestem w ogóle uhonorowana zaszczytem prowadzenia tego wykładu i bardzo uważam, że to jest bardzo dobre właśnie dla młodych ludzi, którzy zaczynają karierę czy kontynuują karierę i chcieliby po prostu wiedzieć, co inni ludzie na świecie robią, jeśli chodzi o matematykę. Także bardzo jestem wdzięczna, dziękuję bardzo. And I think that I will start sharing the screen here. Do you see the screen?
Yes, yes.
Okay, wonderful. Okay, so I was a little bit in doubt, okay, what kind of topic would be appropriate for this particular lectures. And I selected an area when I've been working for a long time, in fact, with several collaborators, which has a very good blend of applications and mathematics, because as you know, applied mathematics consists of two words. There is applied and there's mathematics, okay? And applied mathematicians need to defend both aspects. Okay, so if you talk to scientists, engineers, or whatever, you have to impress them with a applied side of your work, okay, what is good for. Instead, if you are giving a colloquium to mathematician, essentially you have to say something what is really interesting from purely mathematical point of view, and to which extent this application have an impact on development of mathematical tools. And now I'll be trying to convey this message. I don't know how successful I'm going to be, but this is essentially the main theme, okay? So these are a number of collaborators with whom I, been working for a long time, and probably Erdowell is, he's from Duke University, and he comes from the side of application, and he gave a lot of insight in terms of applications. Okay, other people are mathematicians. So I'm going to talk about flow structure interaction and fluid structure interaction. So what it is, it's the interaction between two equations, one describing the flow, so that's typically gas, and structure, it's some plate or shell, and they interact together. Now, what are the applications? Applications are really ubiquitous. You have aerodynamics, when what you would like to do, you would like to control the vibration or turbulence. And we sometimes refer to this control of flutter. What is flutter? Flutter are sustained oscillations. So sustained oscillations, which are, which last for essentially infinite time, if not counteracted, and they lead to the damage of the material and catastrophe, because you have a breaking bridges, breaking wings of the aeroplane. So that's a very important fundamental problem. And the same type of models also do not appear in the large space structures, and were involved in NASA research when you have a solar panels or large antennas. More recently, medical sciences also, they use models of flow structure, fluid structure interaction for example, in cardiology, when you have a flow of blood through the arteries, okay? Blood is a flow, it's a fluid, arteries, it's a structure. And in engineering, a famous example of Tacoma Bridge, which collapsed as a result of a very strong wind. Flutter also has a positive effects, can have positive effects, and that has been explored recently when you think of energy harvesting. So you have oscillations that induce energy. So essentially, if you just take a different point of view, a lot of mathematical development can be transferred into this area as well, okay? So here are just some examples, pictures taken from the web, where you have a flow structure interaction, and that of course depends on the velocity of the wind, of whatever, of a gas. And then you have two regions, supersonic and subsonic. Supersonic is above speed of sound, subsonic is below. So you see these flying vehicles, these jets, okay, which are surrounded by the gas, surrounding gas, and they can, which interact with the structure, with the plate, and can lead to various phenomena such as turbulence or even breakage in extreme cases. Here you have a subsonic level, this Tacoma Bridge, which I just mentioned before, a collapse as a result of the wind hitting really the structure and inducing flutter, which was exactly, we have oscillations lasting for a sufficiently long time to create a breakage of the structure. Okay, so these are examples of subsonic. In case of a fluid structure interaction, when you have a water of, say, fluid, and the structure inside, you have a submarine in the water, for example, and that's an equation which involves viscosity for the fluid part. And here you have an aorta and the blood flowing inside, and that's also, it's a interaction between a shell and the fluid, okay? So you hear about this problem as a mathematician, and then what you're trying to see, can I have some impact on this research? Can I do something? So first of all, we have to identify physical goal. So here it's clear because, essentially the problems are for real and very important to society. A huge step, it's correct mathematical model. And there is a bunch of people working just on modeling, and that's extremely important. And here I'm going to refer to partial differential equations model. They can be different model in statistics, for example. but it depends again on the area of mathematics that you are interested in. And it's important that the models predict the phenomena which can be observed experimentally. So very often there is a forward and back interaction between people in modeling and mathematicians who are trying to derive certain formulas, or not formulas, certain theorems, and see whether the results predict reality. If not, the model needs to be, of course, altered. So once you have a model, then you have to look at the mathematical tools. So you have to set the target goals for this model. So what do I want to show? So like wellpointness of solutions, stability of solutions, or perhaps controlling the solution somewhere. Yeah. So these are all relevant questions. And we need to identify mathematical tools. And here it's very important to do the review of the literature to see what was done and to which extent we can rely on the past experience. And then very often, probably most often, if you are involved with a problem, it happens that the literature or a past literature will not provide you enough of tools, okay? So you have to discover some new mathematical problems. That's a very important step in the process because it allows somehow, it gives you the impact of application on developing some new areas of mathematics. So there are some questions in mathematics, in some areas of mathematics, like for example, harmonic analysis or microlocal analysis. I will give you some example. When you really ask a question that perhaps otherwise would not be asked and leads to somehow opening a door within the field of mathematics, okay? And that's what I call eventually this is going to be stated as theorems. No, and the end of the process is verification, which is based on experiment and some numerics. So that's more or less an approach to taken to the problem. So here, if I go back to a particular model of interest, so when we think of a flow structure, so what are the goals? We want to eliminate this flutter. And as I mentioned before, what is flutter is simply sustained oscillation of the structure, okay, as a result of an effect of the wind or gas in general. Sometimes you cannot do this thing, but you can have impact on so-called flutter speed. So what is it? Flutter speed is onset of flutter. So you have for example, aeroplane, and it is in the air, and at some point starts fluttering, but that depends on the speed. So very important is to be able to control this thing, perhaps increase this flutter speed. And where do you use control? Of course, you have to use on the structure, and not on the gas, because you have really no access, okay? So you have a surrounding gas around. In case of fluid structure, when you have a fluid and the structure, then what you want to do, eliminate or attenuate vibrations, okay? So essentially similar, but the models are different because fluid typically will have a viscosity. In flow, with the gas is Euler equation, which has no viscosity. So that's a big difference, but both problems are, of course, of interest. I'm going to concentrate on the flow structures in this talk. So here is I had a video which does not run at this moment, but you have a flutter effect on the wing of the aeroplane. So aeroplane is just, it's a small szybowiec, Polish, yeah, which is flying and then is affected by the wind. And at some point, this wing breaks, okay? What it is, it's a result of the flutter affecting this wing, okay? So these are the goals that we would like somehow to address. So how do we formulate mathematical question which is going to be pertinent and relevant to this physical problem that I've just described? So in the language of mathematics, what we are going to do, as I mentioned, the partial differential equation is a main here elephant in the room. So we really want to deal with partial differential equation as a modeling part. So we'll have some dynamical. We would like to show that the system as describing the phenomena results in some dynamical system. Dynamical system means that there is a nonlinear evolution, okay, evolution in time. And we have a nonlinear semigroup which describe the process. So there is a question here, of course, of existence, uniqueness, and also continuous dependence on the data, which is Hadamard-Well-Posner's associated with this semigroup. Now, if you think of eliminating a flutter, so what you would like to do, you would like to somehow force this evolution to stability. So you would like to drive to the point of equilibrium, because once you are in equilibrium, then you are there, nothing is going to happen. So that means elimination of the flutter. Sometimes this is not possible. In fact, very often it's not possible. In fact, it can be proved as not being possible. In which case, what you would like to do, you would like to attract this evolution, so to finite dimensional set. Why finite dimensional set? Because it is easier somehow to do things when you have finitely many degrees of freedom. And there is a lot of control theory that has been developed in a circles within the theoretical engineering, which can be used to address the issue. Okay, so these are the mathematical questions. Well, Posner's of a nonlinear evolution, stability, and existence of some attracting sets. Okay, so 3 goals. Here, I just want to give a simply credit for PDE modeling of the system I'm going to study. There have been quite a lot of work done, and particular credit should go to the NASA and UCLA laboratories when you had people under the guidance of Erdol from Duke and also Balakrishnan at UCLA. So I'm going to talk about a very simple model, so that you can decorate this model in a variety of ways, but I want just to describe the main properties. So what is a model? We are going to consider three-dimensional space for upper half space. So the coordinate z, as you hear, vertical is going to be positive, and x and y. And what is happening, you have a wing or plate or structure here described on a, this is black part, okay? So this is a structure which is moving with a velocity of u, which is, and the velocity is exactly related to the speed of a gas in which it is flowing, okay? So we have a thin flexible plate moving with velocity u, and u equal 1 is normalized speed of sound. So if u is greater than 1 will be supersonic, when u is less than 1 is subsonic. And the plate here, I call it omega, with a boundary delta omega is embedded in xy plane. Okay. Now, this is going to be, the system is going to consist of coupling of 2 equations. One of them is a system of elasticity with a displacement u, which depends on t, x, and y. So this is x and y, there's no z because this is on a plane. So this is the wing, say, of aeroplane. And u, it's a vertical displacement. You can write more general system of elasticity when you have also in-plane displacement. That is more complicated, but as I said, I'm trying to just address the main issue for a relatively simple model. So what is important is, okay, you have a linear part, which is a classical Euler-Bernoulli that you learn in elementary courses. And there is a non-linearity f of u. It's important. I will just tell you in a moment what it is. And this plate, it's affected by the wind, and wind is this red part. By phi would mean flow. So this is really potential. This is a gradient function, so potential function. So grad of phi, it's equal to velocity of the flow. And there is this operator, which is a first order differential operator in time and also in the direction of the flow, because x is this special direction in which the flow is moving. And this is so-called material derivative, you can see, or the transport of that flow, and acts as a force affecting the plate, okay? And there is a restriction to the boundary. Here I just change a little bit of notation, so I call by gamma the structure, and by omega the whole three-dimensional space, okay? So this red term has a name, and it's called a realistic potential, okay? So it's a way the flow affects your structure, and might lead possibly to a breakage. Now, what about the flow? If you go over Euler equation and you linearize around this unstable point, capital U, because it's the question is precisely to induce some stability, then you get something that looks like a wave equation, but perturbed by this first order term here. With a Neumann boundary conditions, the Neumann boundary condition on the right-hand side are exactly affected by your structure. So this is an interaction between, like, structure affects your flow, and there are some initial conditions. So in essence, the whole action is between the structure and the flow, and it is through the terms which are referred as transport terms. Okay, so it's a transport of the flow onto the structure, and it is called elastic potential, and downwash is the other way around. So it's a transport of the displacement onto the flow. So if you put everything together, you can see that it's a structure of the problem. It's kind of a pleasantly looking, it's not too complicated, because you have a nonlinear plate. And here is this linearization of Euler equation, but it is really wave equation. And interaction between the two are through the operators, okay, which is transport operator applied to the flow, and transport operator applied to the structure, which affects the flow. So flow is ignited by the vibration of by displacement of a structure, and structure is ignited, is forced by changes of the velocity of the flow, okay? And there are some initial conditions, so we are going to consider the so-called finite energy space, okay? F of U is nonlinearity, and it's pretty important, will be von Karman nonlinearity, which is of a cubic type, but it's non-local, and it's represented by so-called hyperbolic Airy stress function. What is important to note is that both equations are of hyperbolic type. This is a wave equation, it's a classical hyperbolicity, which you can write as a hyperbolic system. And the first equation, it's a Euler-Bernoulli, which has infinite speed of propagation. So in that sense, doesn't have a hyperbolicity, but it's from point of view of regularity, it's a hyperbolic-like model. So there are no regularizing effects, parabolic effects. So what is nonlinearity? Nonlinearity is a von Karman von Karman stress, and how it is defined. It is defined through the von Karman bracket, the square part, and this is products of a second derivatives of the functions. And what is going to be important here, the coefficient in front, that you have a 1, 1, and -2. You will see that this magic later will be taken advantage of when talking about some methods of compensated compactness. And there will be some cancellations or compactness induced precisely because of this, of the physics of the problems. And this is not just any linear combination of a second derivative, but it is exactly Airy stress function. And it is defined as a solver of a biharmonic problem, but fed by nonlinear effects on the right-hand side. So this is it's a little bit related to Monge-Ampère equation. So this is our nonlinearity, cubic and non-local, okay? And this models very well large deflection of the structure. And that's important because you are precisely concerned with the deflections which can be large enough to lead to the breakage. So that seems to be a correct model. So now what do we want to do with this system? We want to ask a question of well-posedness of finite energy. Finite energy is just a matter of language, often refers to so-called weak solutions. So there are some natural energy function resulting from the derivation of equation. And these are called weak solutions. So this is essentially the same. What I want to emphasize is this is a hyperbolic-like system. So you don't have regularizing nonlinear hyperbolic-like system. You don't have regularizing effects that allow you to get the estimates or compactness in a simpler way. So this is a challenge. And after we have a well-posed system, well-posed meaning Hadamard, which means existence, uniqueness, continuous dependence. then you want to see what happens with a long time behavior when time t goes to infinity. Okay, and that means a theory of dynamical systems. So these are the goals set for the problem. So what do we start? We start with a baby step, which are so-called energies. So when you have equations, okay, one is looks like a wave-like, another plate-like. So what you do, the first step is probably natural for most people who had some elementary exposure to partial differential equations. So you try to derive some energy relation by taking a product of one equation, say wave equation, you multiply by velocity, the same thing with a plate, and you do integration by parts, and then you will see some nice cancellation or simply do not total derivatives, and you get energy. So what is going to happen is the following. So for the plate or structure, the classical energy is, well, you take a velocity of the displacement. Okay, this bracket means L2 norms. And also momentum. This is Laplacian of U, so that's a momentum. That's a classical energy associated with any plate equation. Okay, there is a non-linearity, so here I'm not going to be spend much time, but just as I said, this is a cubic type of non-linearity. So when you write it down, energy of the plate, which also contains a non-linear term, so this will be a fresher derivative of this non-linear term will be corresponding precisely to this non-linearity f of u. So as you see, this is related, v of u, it's a Airy stress function. So we have here four essentially functions, which is it's non-linear because v of u itself is cubic. Okay, so it does not have any definite sign because of possible perturbation by this term f sub 0. And now you look at the flow equation, so that is related to wave equation, and phi it's a denotes a potential function, and phi sub t is the velocity. So you see that we get, like for wave equation, you get the first two terms which are very, very familiar, but then this effect of the wind translates into additional term with this term u square and derivative of the flow in x direction only. But what is really happening here is that if u is greater than 1, okay, this is here, everything normalized, you can see that the energy of the flow has no topological properties because it becomes negative. You cannot say that you have some norms, say L2 norms for velocity and for the gradient bounded, because you have here another term that destroys entirely positivity. So we call it this is degenerate. So this is already effect of the wind, okay, this capital U of the flow, and you see that velocity is going to be very important. Then of course you have some interactive energy between plate and flow. Now what happens if you add everything together, then you call this is an energy of your system. So energy of the plate, energy of the flow, plus this interactive energy. So that's a quantity. And now this quantity is constant over the whole time. So this is something that looks very, very nice at the beginning because the derivative is equal to 0. By the way, these calculations are completely formal because they are obtained by integration by parts, assuming that you do have solutions which are smooth enough and you can justify. So construction of solution is, of course, here a very important and big question. However, based on some experiment, I will mention this more before later, one would expect a certain stabilizing effect of the flow on the structure. Okay, has a stabilizing in the stabilizing. So you know that if you fly the aeroplane and if you go faster and faster, at some point the turbulence stabilizes. Okay, and that is of course observed by experimentalists, by scientists. Now, if you have here that the relations that energy is just conserved all the time the same, there is no way that you can see any stabilization from that kind of analysis. So what is happening? You have like a black box, everything closes, but as I mentioned a moment ago, that energy of the flow is not necessarily positive quantity, so there is a lot of information hidden. So what you need to do, you need to really break down this box and go and understand what is going on, what are the interaction inside, okay, and how can we get information about the phenomena we are interested in. And phenomena it's related, for example, to some stability effects of the flow on the structure. So the action is inside the box, okay? So this energy method, which is very nice, very popular, everybody does takes you nowhere because you cannot really anything, and not even well-posedness or boundness of solution because you don't have a definite sign for the energy corresponding to the flow. And certainly there is no site of any dissipation. So what is here, like in the Navier-Stokes equation, has been discovered quite recently, that there's so-called anomalous hidden dissipation, that in this case will be due to the dispersive effects of the flow of the flow, because this is half plane. So even if we have a derivative of the energy equal to 0, there will be some way of convergence to 0 of the solutions, okay? Which somehow is counterintuitive, just because the information is inside the box. So our main goal is precisely to understand this thing from a more microscopic point of view. Now, talking to practitioners, okay, who are doing a lot of experiments, what they were telling us, based on experimental study, that you should be able to eliminate the flutter at the subsonic level. So if you use less than 1, for example, the bridge, you should be able to eliminate by using some dissipative controls, okay? However, in general, there is an expectation that asymptotic behavior, it's reduced to a finite dimensional attracting sets, okay? So if you wait long enough, so for any values of a wind, you expect that your solutions are going to be attracted, described by finitely many degrees of freedom. And these attracting sets, so-called attractors, can be chaotic, okay? So might not necessarily be nice structures, but they will be finite dimensional. So, okay, this kind of expectation based on experimental studies will lead to mathematical challenges. So how can I see that I can eliminate flutter, or which is, as I mentioned before, that's related to some stability property, when there is no active dissipation, neither on the flow nor the structure. Nothing is dissipated. You don't put any damping, okay? And how can I get an attractor when we don't have any compactness? Why there's no compactness? Because the dynamics is of hyperbolic type, so the flow solutions don't have a, semi-grooves don't have a compactness property. And the nonlinear term also not only has no compactness, but even locally Lipschitz property is questionable. And then we have this potential degeneracy of the energy function. So we need to understand, okay, how to deal with perceived dichotomy with respect to what we are supposed to observe and what we really do know, can see from the model and mathematical tools. So here I want to go very quickly. So this type of research has attracted a lot of attention in the past, and there are many, many papers written by mathematicians. But however, here I'll give you a list of references. However, the models which were considered were related to regularized models. So they were extra regularizing terms. So this way, well-posedness could be shown. However, effect of stability of the flow in the structure, not because by regularizing you are making these models heavier in some sense. And that was not possible to show. So that's why we work with the original models. There are no shortcuts by regularizing terms, okay? Regularization typically leads to added derivatives to the velocity of the plate. So we work with the original model because regularized model is smoother solution by adding one derivative and making nonlinear term compact, simplifies the analysis of well-posedness, but does not answer the physical questions motivated by physics. Instead, the original model, if you just look a little bit deeper, leads to a variety of interesting mathematics. And one of them is the development of harmonic analysis, because just to deal with a supercritical nonlinear term, you will see that there will be some harmonic analysis used. And also what is interesting is that we don't have any dissipation, so we don't have a Lyapunov dynamical system theory. So perhaps you heard the thing, which would make your life, of course, simpler, because there's no dissipation, and we don't have a compactness. Okay, so these are building blocks of dissipativity and compactness of any sort of a dynamical system theory when you want to show existence, stability, or existence of attractors. So as I already said, new techniques in mathematics, which you have to somehow open yourself to, are, of course, in addition to partial differential equation, but harmonic and microlocal analysis, and also some theory of the weak Hardy spaces. Probably you had this thing in your courses in analysis. These are the spaces like Hardy H sub P or Lyapunov spaces. And then on the other hand, on dynamical system theory, you have to deal with the theory of attraction for non-dissipative system. There are a lot of books for dissipative. And here we don't have effect of dissipativity because of this term, which is capital U, applied to the displacement of the plate. That's what creates lack of dissipativity. Okay, so these are the issues. So let me just go over first qualitative results, what we are able to show. We will be able to show that solutions do exist in finite energy space. What finite energy means is that this quantity defined by energy are bounded, they are all well defined. And it's very interesting to see that that result will be false for the linearization of the model. So the nonlinear effects on the structure play critical role. And then we'll be able to show that with the flow data, which are compactly supported. So what does it mean? That's a realistic assumptions, because you want really to look at the effect of the gas, okay, on certain finite domain, okay, not on a whole sky. Then we can show that without any dissipation, solution converge to a finite dimensional set, which in fact is even becomes a smooth. So that's going to be an attractor for the structure, okay? So solution of the structure, not solution of the whole system, because you don't expect flow to have this property. In the subsonic case, with some feedback control implemented on the structure, we will be able to stabilize this solution to stationary states, which means that flutter can be eliminated for the subsonic model, as predicted by practitioners. So what I'm going to do perhaps is not necessary for some of you, but I thought that might be a good idea, is that we go over some basic tools in abstract dynamical system to see what kind of properties are needed in order to prove some of the statements which I made just a moment ago. So let me start with an abstract equation. So by Y, we say we have a state component, and we have a just evolution described by some operator, nonlinear operator acting on Y, with some, of course, a domain on a Banach or Hilbert space and with initial data. So we will be dealing with a concept that A of Y generates a continuous semigroup on H. So I'm assuming that this A does not depend explicitly on time, otherwise would be an evolution, not necessarily semigroup. So we will have to understand what kind of conditions guarantee the existence of this kind of property. Then we'll talk about strong stability of the semigroup, strong stability to an equilibrium. Equilibrium is defined as a stationary point when this capital A, this operator, has just a, the dynamics disappears, as you see. And then we'll talk about attraction by finite dimensional attractor for the semigroup. So these are the concepts I want to go over very quickly. So starting with the semigroup, generation of a semigroup. What is a semigroup? So semigroup, we know that this is an operator which at time t equals 0 is just identity, has an evolution property. So if you take a semigroup at the point t plus s, it's the same thing as it's a bounded operator. So semigroup acts on an element of a space. So you can walk for S seconds and then followed by T seconds. It will be the same thing with a reverse order. And there is a property of continuity at the origin, which means that semigroup for in any initial condition, when T goes to 0, then the semigroup goes really to identity. Keep in mind one thing, perhaps I should mention, that this is only strong continuity. There is no uniform continuity, because if it's okay, uniform continuity would mean that operator, this capital A, is bounded, okay, which is not the case of partial differential equations. Okay, and strong continuity at the origin and evolution property tells you that you have a strong continuity at any point T. Okay, so this is a. So here evolution property simply says that if you start at T equals 0, then you just walk for, say, S minutes. Okay, you stop, take a break, and then you continue point T for another T minutes. It's the same thing as you would be just going for time S plus T. Okay, so it's very, very elementary. Now, what is strong stability? Strong stability simply means that if you take any initial condition in your Banach favorable Banach space, so this operator, when applied to this initial condition, and you consider time T going to infinity, will converge to some point of equilibrium. Okay, so we have a Y0, it's taken to point of equilibrium. So this is called strong stability, and equilibrium is defined as a kernel of your generator. Now, absorbing ball is another important concept in theory of dynamical system. So what is the absorbing ball? As the name says, it's a ball that absorbs all the trajectories. So to have an absorbing ball, in fact, typically it's quite difficult to show that there is one, because it really involves calculations, but you have to be very careful how do you do this thing. But what it says that there exists a number R, big enough, and a ball with a radius R in this Banach space, such that all the trajectories corresponding to all initial data are going to be in this ball for some time T0, after some time T0, which might depend on initial data though, but capital R doesn't depend on initial data. So it's a universal ball for everybody. Everybody has to get into that ball, okay? So this is a called absorbing ball. And what is attractor? Attractor is more constrained concept than absorbing ball. Typically, if you have attractor, you have also absorbing ball, but not the other way around. And attractor, it's a set that is invariant for positive, essentially invariant gives you invariance, a semigroup applied to an element of attractor, it's in attractor, and an element of attractor can be obtained as a image, is in the range of the semigroup, and then has attraction property, which means for any bounded set in a Banach space, the distance between solution itself, set of solution originating in the set B, and attractor goes to 0. So what it means that all the trajectories from this bounded set eventually will end up in attractor. So by the very definition, because we are talking about a strong convergence, attractor is compact. Okay, so attractor is more restrictive. So we have this property. So what you want to see from point of view of the classical analysis of a semigroup to see what do we need in order to show these properties. Okay, so if you look at the dynamical system, which is described by some linear operator plus nonlinear term, which is very often the case. So my A of Y is sum of the two. Okay, let's take this case as a representative at this moment. So the classical results will say, so what we want to get a generation of a linear semigroup, of a nonlinear semigroup. So if A generates strongly continuous linear semigroup and capital F, it's locally Lipschitz. Okay, so we have a local Lipschitz property on that space. Then you look at the variation of parameter formula which defines certain integral equation, and you look at the solvability of this equation for y. Okay, and then you can use one of your favorite fixed point theorem and show that locally for time t restricted to some possibly small time, solution does exist in the space. So that's a kind of a, if you look at the Pazzi book or Cato's book, okay, one of the most elementary results on existence of the local solution. To get a global solution, so it means that solution does not depend on a horizon, then you need some a priori bounds, which means that you have to get some estimate on a solution for all time, which only depends on initial data. And this usually you obtain through some energy calculations, but you have to be careful to work on a solution which exists, okay? Existence of local solution is guaranteed by this fixed point. So bottom line is that what you want from this your nonlinear term, if it's locally Lipschitz, okay? If it's not locally Lipschitz, then it's a completely different ballgame, and the methods depend really on the particular partial differential equations, and there is no really unified theory. There are certain classes, and I'm going to talk about it. So you have to do something very special, but this is a classical framework. So as I said, what you need locally Lipschitz property, which is stated here explicitly, and you need a priori bound. Now, what is happening for the models that we are interested, because of the nonlinearity on the structure, this number one fails for the flowered structure. So we have number two, at least for the subsonic case, but number one fails. So you have to do something. So that immediately tells you that whatever you'll be doing, you have to discover something that is not obvious just by referring to standard sources. Now look at strong stability. So I'm going to work with the same system, which is AY plus F of Y. And then, of course, here, what is needed to get strong stability, you need the dissipativity of the generator. So you want the dissipativity properties, okay, of this linear part. And then you want a so-called strict Lyapunov function. Sometimes it's called a unique continuation property, namely that if energy is equal to 0, then solution is equal to 0, okay? Because it tells you that you have we reach exactly the equilibrium. And the compactness of the semi-group, all compactness of F. Now, what happened for the flow structure models that I mentioned, all the sig from 2 to 4, all the sig fail. Okay, we do have energy identity in some cases, but we don't have other properties. So again, it's interesting, how can we overcome this difficulties by developing something different? Now, for existence of global attractors, the standard theorems that you find in Ładyżeńska, Hell, Babin, Temam, Wishik, many sources. I have references at the end. Is based on so-called decomposition of the evolution into the sum of the two. The first one is uniformly stable, so it means it goes to 0 with a certain rate, and second one is compact. Okay. So now again, this works well when you have some parabolic effect, so the semi-group is compact itself for time t positive, or you have non-linearity, which gives you a compact effect. Okay.
I have a question. I somehow got lost. As the semi-group ST, what is the generator of the semi-group? A or A plus F?
A plus F.
A plus F. Okay, thank you.
Yeah, all the time, A plus F.
Okay.
Okay. So that's a good question, because sometimes this U sub T, which is here, another operator, is very often a generator of A itself. Okay, but it has to be stable, yeah, which is not the case. But more generally, you can manufacture someone that is stable. And the compactness here, it's a very, very critical thing. So if you have
so one more question. So if you don't have Lipschitz condition, so how do you get ST?
That's exactly the problem I'm addressing.
Oh, okay.
You have to do something.
One has to do something. Okay.
This is something that if you have, you have a model, then you can start working these tools and you get results. I'm trying to make is that these standard things do not apply. Okay, and one of them that you don't have a Lipschitz property. Okay, there must be something else. Okay. But if you have the thing, then you have absorbing ball and you have asymptotic smoothness, then you have a distance of global attractor. So in fact, you helped me to address this question that if I have a uniform stability of A itself and compactness of F or smoothing effect, then I'm done, but we don't have this. This will be sufficient condition, okay? This kind of a nice situation. So as I said, so main findings qualitatively that we have dynamical system and we are supposed to eliminate flutter in subsonic case and get attractor in more general case. And main obstacles are lack of compactness of F, okay, critical nonlinearity, even local Lipschitz, and lack of damping because the energy is equal all the time constant. So you don't have any dissipation whatsoever, nothing goes to zero, at least from the first look, and loss of ellipticity. So we call these things that these are attractors if we want to show this thing out of thin air, because there is no coming from things. Here I'm going to go, because I see that my time is running out. I go quickly through the basic theorems which were shown for this particular model, and we start with well-posedness. In fact, we show that we do have well-posedness for the whole model, for those flow structure interactions. So there is a local and global solution, and in fact, for smooth data, it's even smooth. And then we also have a finite dimensional attracting set, but for the structure only, without any damping. So that if you take just a plate solution, so you can show that all this trajectory converge uniformly, so distance going to some set which is finite dimensional and in fact smooth. And the third solution is related to strong stability, which means that but it's only for subsonic case when your energy has a good topological property, that solution converges to some points, stationary points. So these are the three results I'm talking about, okay, well-posedness, attractors for the structure, and strong stability for subsonic case for the whole model. So flutter can be eliminated. So these are just numerical illustrations that you start with a displacement which is pretty deep, and then you end up with something that is modulate. Probably I prefer to have this picture here. So you have a first displacement, okay, oscillating, but eventually converge to some one of the stationary states, okay? And you have another situation when the flutter is maintained. So it stabilizes a little bit at the beginning, but at the end, behavior is that we have still oscillation. We have either periodic orbits or some limit cycles. So it means that in that situation, flutter remains, okay? So, but it can be described by finitely many degrees. Here I am going to leave for you. So proofs of these results are given in the following references, and then one of the good probably sources, it's Oberwolfach seminars. We are giving a talks, at Oberwolfach for 1 week, and there are all the details given, and this is a book which contains many details. Okay. So now, why it is? Want to talk a little bit about mathematics. So why it is interesting? Because we have a non-linearity of the plate that precisely this locally Lipschitz property works, and we don't have any dissipation. And this requires some new methodology for dynamical system. How do you work with non-dissipative system? As it has been developed also partially in my joint work with Tuyashov, and it's in a memoirs volume on 2008. Okay. And what is important that we are working with a correct PDE model, which is nonlinear. There is no diffusion, there is no regularizing effect, and that's what solves flutter problem, can show the flutter, in fact, can be eliminated. So perhaps here I'll just show you a little bit, okay, so how do we attend well-posedness? So we start with this energy function, and as you know, we have this energy balance, which says that this is constant all the time, okay? So this is black box, we cannot do anything about it. However, energy is something, so this is exactly, so we have a bad energy, but we have a good energy balance. Now, other way of looking is, okay, let's change an energy and see what happens. Perhaps we can have energy that represents topology of the spaces which we work. Okay, so we need this. It's just a question of finding smart multipliers. And we can do this thing. So we change energy of the flow, which is right now completely positive, but energy balance is destroyed because you have this propagating boundary term, which has capital U in front. And so this is a really disturbing term because we have to somehow address the issue, how we are going to deal with this thing. Okay, this is unbounded term. Why? Because of the traces. The thing is that if phi it's in H1, so that exactly has one derivatives, so that x derivative of phi will be L2, and you cannot take a restriction to the boundary, as you know. So L2 functions might not have traces. That's a classical result in analysis. So you have to address this thing, somehow. So these are the topics that are bringing you mathematical question for each part of the system. So how do we do this thing? We have to deal with the superlinearity of the plate motion, okay? And we have to find some results for this, just of interest for this equation. And we have to also propagate this integral to understand behavior of this integral term, and not only to show that it's well-defined, but also that propagates stability. And you don't see this thing in terms of any kind of, sign condition or so. And this leads to two mathematical questions, okay, which can be completely independent of the original model. One results for the structure and one for the flow. And what it is? For the structure, it's essentially understanding of the von Karman nonlinearity in the plate equation, okay? And in fact, just to give you an idea, this question, which is completely right now just for the nonlinear elasticity, it has nothing to do with the flow structure, doesn't have to do. And it's a script F, it's Airy stress function was defined before. So what is happening here? We do have a situation when existence of solution was known for a long, long time. However, uniqueness and continuous dependence was open problem. And I'm here quoting people like Karman, Lyons, Lagnese, Sierle. So you can find this thing for a dynamic case, which is here, was an open problem. And that has to do with regularity of the Airy stress function. So now we are just focusing on the regularity of Airy stress function because that is something that we would like to see as having some sort of a good estimate, good properties to describe the flow, to describe the displacement. Here, I don't know how technical you want to be, but the point is essentially that if you do classical analysis, then you get that this nonlinear term is not in L2, but is in some Sobolev space on negative order, okay? And what you would like is delta is positive, okay, so it's negative. So what you would like to have is delta to be, to eliminate delta equals 0. That is not possible because we can, it shows as being not, result is negative. So we deal with supercritical nonlinearity. So what is really solving the issue? It's a compensated compactness criteria, which is based on the work of Pierre-Louis Lyons and Meyer. And when we show that we cannot show more integrability of a Airy stress function, but more differentiability, but we can show more integrability. So what we can show that Airy stress function has two derivatives in L infinity, rather than having above, say, 3 derivatives in L2, which would give by Sobolev embeddings the same inequality. And that really saves the day because this kind of an estimate here allows you to treat existence and uniqueness and continuous dependence for the plate. And get you the result also to solve the open problem for the von Karman system. What does it contain of? It's, as I mentioned, what a compensated compactness. Okay, so what is compensated compactness? There is some cancellation. That's compactness tells you that if you have a bounded sequence, you can extract strongly convergent subsequence. Okay, so you don't have so what you can get here for this part, you have to use the structure of this Airy stress function in order to conclude that in fact this bracket, which is here, which typically would act from H2 because we had two derivatives. Okay, so if you multiply two L2 function, you get L1 function, but in fact, it's a little bit better because this is a Hardy space which is embedded in L1. And what is Hardy space? It's a space that Risch transforms are bounded from H1 to L1. So this is topologically L1 norm, but has a structure. Okay, and that was the main thing. And then once you have this result, then you can use the theory of a biharmonic solvers and take this H1 to Lizorkin space, which has four derivatives. If you work on L1, then you never get four derivatives back, but on Hardy space, yes. And this is a theory in Runstein-Sickle. And then you go to Hardy Sobolev embeddings and you get W to infinity. So these are the three steps. Here I don't have time, but I just want to mention that what it's really is this membership in Hardy space is related on a cancellation, really on a structure of this von Karman bracket, because there is a result due to Kaufman and Mayer saying that if you have a bilinear form which takes you to L1, this form will be in H1 provided that the symbol is going to vanish. Symbols, these are just a Fourier transforms, okay, for a Fourier velocity. And what is happening in our case, magically, if you take a symbol of the bracket and you have this coefficient 1, 1, and -2, z is equal to 0 when you take the same frequency. So you see that's a very eventually at the end is a very elementary algebra, but it's really harmonic analysis result, which tells you that bracket is in fact in Hardy space. If it's in Hardy space, you have a good elliptic theory that takes you to the Lizorkin space and embedding theory. And it is a joint work, in fact, with Daniel Tatar from Berkeley, and we were able to show that the original von Karman system has has a good evolution, which is strongly continuous and unique or arbitrary. For the flow instead, if you want to deal with this integral that's propagating, again, what you need to have some estimates of the integral, which originally is a product of L2 function in H minus 1/2 YZ, because UT is in L2. Phi was in H1, but X derivative will be in L2. But if you take trace to the boundary, then formally applying trace only get -1/2. So there is no way that you could deduce any sort of a well-posedness from that product. It's not well defined. So what you have to do, you have to go to the regularity of the wave motion and ask a question whether this element phi has some better property. And in fact, by some integration by parts, you can reduce the question to ask the time velocity, the velocity of the flow for the D'Alembertian, for the Spertor wave equation, okay, with a given Neumann data, has a derivative in -1/2. Okay, that will be enough because a new X is in H1. And in fact, this is a case, but just to give you an idea, what it takes so-called micro-local analysis. You cannot get this by estimate. When you have to look at the sectors, which is, I'm about to finish, sectors, characteristic sector, hyperbolic and elliptic. So this is a tool which is using micro-local analysis, and it's very successful here. I know that I'm late, and I really do not apologize for this. I just want to go to the conclusion. That we show that flow provides a hidden dissipation because we get this convergence, and structure provides hidden asymptotic regularity on the attracting set. And propagating this property, it's a main challenge of the problem. So in subsonic case, we are able to eliminate Flutter. In general case, we are able to reduce to the finite dimensional structure. So we have a finite dimensional problem at the end for the structure. There are many open problems. Many open problems involve different boundary conditions for the structure and the flow. Transonic case, when capital U is equal 1, it's a different problem because there are shocks. And also you can use a localized and boundary damping as a method of including some dissipation for the strongly stable. And I will just have here some references that I leave with you. And I would like to thank and apologize for taking a little bit longer.
No problem.
So thank you very much.
Thank you very much. Are there any questions?
Okay, so every time you were talking about attractors for some equations, they were finitely dimensional subspaces. And why does it matter that they are finitely dimensional?
The reason is the following, because if they are finitely dimensional, that means that, you see, what we are showing that the oscillation of the structure, okay, asymptotically converge to this attractor, okay? An attractor consists of this chaotic, but say periodic, for example, functions, okay? And now eventually what you would like to do, you would like to eliminate this altogether. Okay, so then you have to use some tools of a control theory, which could reduce the thing by additional action on the structure, which could eliminate these elements. But these are finite dimensional theories. So knowing that the structure of this oscillation is now finite dimensional asymptotically does help because it allows to use these methods. So it's very critical to know that you have only finitely many degrees of freedom. There is also another area of interest here, which is was developed by Edris Titi and Temam not a long time ago, which and Ładyżeńska started with the Ładyżeńska work, which shows, precisely shows that gives criteria for the asymptotic behavior to be characterized by finitely many modes. And the goal is the same, that once you know that there are finitely many modes, you can use also approximation theory to approximate the solution. And you know that eventually you are going to get a good approximation because the final effect is finite dimensional. In some sense, it's easier said than done, because saying finite dimensional, we are not saying that these are just eigenmodes, okay? So there are finitely many elements describing, and it takes quite a lot of effort to characterize them. That is being done now, okay, by numerical methods, but also by the theory of periodic functions, to see what is the basis in this attractor, okay? But finite dimensional structure is very important because it opens possibility of entering this set through finitely many degrees of freedom. Did I answer your question?
Yes, thank you.
Thanks.
Any other questions or comments here on site or online? Perhaps I have a question. I'm not sure if it's a well-posed question, but it's a very general. Your research comes from problems in engineering, for example. So do you have precise suggestions for engineers how to develop bridges? I mean, to build bridges, or I mean, because how to eliminate Flutter? You know?
Yeah, this is a very good question and extremely difficult, because obviously what we can say is that is possible to do under certain conditions, under certain values of the parameters. But then you have people who actually do this thing because obviously, you know, the Flutter was a problem that exists, you know, as long as, I don't know, almost civilization. So they were methods. However, just to give you an idea, in the case of Helios, this is famous accident when in NASA, when the Helios spin structure collapsed, okay, it was about 10 years ago. And they didn't understand what was going on. And we, in some sense, helped them to understand what was wrong, what they were doing, because they were modeling this structure by a parabolic system, assuming that there is some structural damping in the structure. And therefore, the model is parabolic. And as you know, in parabolic systems, the spectrum, the eigenfunction behave in a certain way, so they are contained in some triangular sector. So essentially, they escape to infinity. Now, what we are able to show is that it's not the case, that really the structure is a hyperbolic. So it has it is, even if it is stable, the eigenvalues are very close to imaginary axis. Okay. And now if you are trying to control, say, 100 eigenvalues because you think that's what you want to do, like engineers are usually finite dimensional, then by doing this, you are perturbing the remaining, say, infinity minus 100. And if they are very close to the imaginary axis, they can go to the right, causing instability. In parabolic dynamics, this will not happen because they are so far away that perturbation theory is pretty stable, and you would not be able to do the things there. But here the modeling was definitely wrong, and they understood, okay, so we cannot really start with a finite dimensional model, just chopping eigenvalues and believing that that's a parabolic effect for the whole thing. You have to start working with an infinite dimensional system, design control theoretically, which is going to do whatever you want to do, and then approximate this control. And that was working. So that was one of the success stories that, in fact, resulted in a quite generous funding from NASA and also from NSF, because it was a concrete problem. That not that we went to the really field work and did the work, but at least were able to explain, okay, why this was not really good modeling, and you have to change a way of approaching. So this is the same thing here, because there are a bunch of parameters which I, of course, don't discuss, and they are probably of less interest in mathematics, but you want phenomenologically to see what is possible, what is not possible, okay? And we know that if you take a subsonic velocities, then a strong stabilization to the equilibria is not possible, okay? But you can reduce to finite dimensional region, which requires additional intervention from practitioners, from finite dimensional theory. So I don't know whether but it's a main question. It's a main issue. What we are doing, how relevant it is to people who are, trying really to do the work. Very good example. It's also work by Filippo Gazzola from Milano, because he also works with a bunch of people who are engineering department, and they do tons of experiments and also numerical calculation, and they were fixated with Stockholm average. They try to understand which modes were responsible for the collapse, and they have a very interesting movies about this. So this is the way mathematics somehow is not that solves the problem, but gives some insight into the problem, and perhaps direct, some ways, roadmaps, what to do and which way to approach. And as I said, modeling is critical, because sometimes we can say that this is a wrong model. Here I didn't have time, but I could show you why can we say that this regularized model there's no way that they can even predict Flutter. So they are not the correct models. So they get solutions and everything, existence uniqueness, but nothing beyond that. So we have to work harder on existence, but to work with a model that is of relevance to the phenomenon. Okay.
Thank you very much. Are there any other questions?
Yes, I have a completely different question. So regarding the modeling of Flutter, for example, what comes into my mind, just it drops in, is the method of stochastic analysis, calculus, and something like stochastic integration. Could this be applied in this field? I haven't seen any stochasticity, but I guess there might be some relation to this.
Yeah, okay, this is not a stochastic model, obviously, but there's a lot of perturbation theories that could be developed for this kind of problem, in a sense that precisely to show that if you have some uncertainties which could be described in the model, they were not taken into consideration in what I presented, but that has been done for some sub-problems of this particular model, and to show that within certain range, okay, the results are still remain true, and to show the bands on it. This is not a stochastic, this is rather uncertainty.
Yes.
And there are some optimal control theories, which exactly do know, like H infinity, which allow you to construct the controls subject to uncertainty within certain bound, okay? Which is not a stochastic approach.
Yeah, I understand that this is not a stochastic problem.
No.
But,
But it could be in principle. The question is, of course, it could be, because then the model is completely
yes,
different.
yes, and the EQ calculus has the wonderful property that it strongly simplifies some hard calculations, because you have to involve structures like semi-martingales or special cases, Brownian motion, and then you are in the heat equation system.
We don't have a heat equation here,
Yes, yes, yeah, I know, I understand. But perhaps this could be a very useful approach to attack such a very complicated problem by means of stochastic analysis. But this is just a very, very vague guess.
No. Oh, yeah, of course, that there are some elements of a stochastic control theory that enter here. For example, if you look at the problem of a stabilization, okay, and so even for linear models, and you have so-called Riccati equations, and the Riccati equations are deterministic, but they also solve the stochastic problem, as you know, because you just minimize expected value. So there are tools in control theories that involves to what we are saying. In a sense, is simplified because you have a more global quantities to work with. And that could be used, for example, even at the finite dimensional level. And I think that's a quite good suggestion, because then system becomes simpler once you have a finitely many degrees of freedom. So you have to have a model. And then having a stochastic model would be very nice, because then what we do, we just reduce to that structure, and then from that point of view to control, obviously the stochastic analysis is much more doable than starting with the whole thing. So thank you for this, yeah, definitely.
And it might be even possible, because you mentioned stochastic optimal control. This is a huge field in mathematical finance, and there's a lot of papers available in that.
Oh no,
field.
it's infinitely many papers. I know that.
Perhaps that could be useful, yeah. But I'm not an expert in this field, of course.
No, so that's what I'm saying. It definitely opens things, many things that can be done, by taking this point of view. No, very good comment.
Okay, thank you. Thank you very much.
Okay, are there any questions still? Well, if not, let us thank again the speaker.
Thank you.
Thank you very much. Thank you very much. Dziękujemy Ci, Ireno, że byłaś tutaj z nami.
Ja, dziękuję bardzo.